A neural network is not a tiny brain. It's a stack of grid multiplies that folds space, like folding paper until the answer is easy to cut out. That one swap in your head explains almost everything about how these things work. By the end, you will know why a neural net needs that fold at all, and why everyone who builds them fights about depth instead of width. That's one fact underneath both, and it's not the fact that you'd guess. Start with where the brain picture comes from, because it's not crazy. The earliest neural nets borrowed a word from biology, and the word was neuron. So people pictured tiny cells lighting up, thinking. But hold the two things side by side. A real neuron is a living cell. It has structure, chemistry, timing, branches, all of it doing work. The piece a network actually copied is insultingly small. Take one number in, multiply each one by a weight, add them up, pass the total through one simple bend. That's the artificial neuron. The whole thing. A scientist at MIT named Tommaso Poggio, who has studied how brains and machines learn for decades, was asked this exact question: whether the brain comparison holds up. He called artificial neurons caricatures of biological neurons. That's the honest word. The network kept the cartoon and threw away the cell. So if it isn't a brain, we need a better picture, and the better picture is a machine. Here's the machine. A multi-layer network is a function. You feed it a list of numbers, it hands back a different list. And every layer in between does the small, dull, exact thing. It multiplies your numbers by a grid of weights, and then it bends the result. Multiply, bend, multiply, bend. That's it. Now, why the bend? Why not just stack the multiplies? Because if you stack two grid multiplies with nothing between them, the math collapses. Two grids multiplied together are just one bigger grid. So 1,000 layers with no bends would still only draw straight lines through your data. Every extra layer wasted. The bend is what saves it. After each multiply, you pass every number through one simple rule. And the popular one is about as plain as it gets. If the number is negative, set it to 0. Otherwise, leave it alone. That single kick is what stops the layer from collapsing into each other. And once they don't collapse, each layer can do the thing this whole video is about. It can fold the space your data lives in. So picture your input as a flat sheet of paper with your data scattered across it. Cats over here, dogs over there, all tangled together. One layer of the network folds that sheet once. The next layer folds the already folded sheet again. And here's why folding is the right picture and not just a nice image. Fold the paper a few times, then make one straight cut with scissors and open it back. That single straight cut becomes an intricate, jagged shape of the original sheet. You made a complicated boundary without ever drawing a complicated boundary. You folded until the heart shape became an easy straight line. You cut the line, and the folds did the rest. That's exactly what a deep network does. It never draws the complicated boundary between cats and dogs directly. It folds the space layer by layer until boundary is a straight cut, makes the cut, and unfolds it. The math here really transfers. The number of separate, flat pieces the network can crave its input into grows the same way the layers of paper grow where you fold, which is the whole next point. Count the layers of paper as you fold. 1 fold, 2 layers. 2 folds, 4 layers. 3 folds, 8 layers. 10 folds, you are trying to cut through more than 1,000 layers at once, which is the real reason you physically can't fold a sheet of paper much past 7 times. The layers aren't growing by 1 each time, they are doubling, because every fold acts on everything the previous folds already made. Now bring that back to the network, because this is the fact I promised. Adding width is adding more cuts to the same sheet. Useful, but it adds. Adding depth is adding more folds, and folds double what's underneath. So depth sits right where the doubling happens. There are functions a deep network can handle with just a handful of units per layer, then a shallow network cannot match unless you make it impossibly wide. That was proven cleanly about 10 years ago. Width adds, depth multiplies. That single difference is why these networks are built tall. Now the other side, because this story is not finished. A couple of years back, a new design showed up called a Kolmogorov-Arnold Network. That's how it's pronounced. Instead of fixing the bend in advance, it moves the bend onto the connections and lets the network learn the shape of each bend itself. On some physics-style problems, the early results looked strong, and a lot of people got excited. Then a separate group ran their fair test, matched the two designs on equal parts and equal computing power, and the ordinary network won on most everyday tasks. The challengers' edge showed up mainly on symbolic math, the kind of problem where you want a clean, readable formula out of the other end. And even that mostly came from one trick you can bolt onto an ordinary network too. Back then, it also trained about 10 times slower. Faster versions have shrunk that speed gap, but the plain design still trains slower. So for raw speed, the ordinary networks, the bigger shift is where this design found a home. The Challenger didn't replace the folding machine. It found a different job. Where it has really taken hold is science, helping a researcher pull a readable rule out of data instead of a black box in physics and other places, where the goal is to understand, not just to predict. So here's what to actually carry out of this. Drop the brain. When you hear neural network, picture a stack of grid multiplies that folds a flat space until the answer is easy to cut out. That picture tells you why the bend matters, why depth beats width, and why the boring stacked multiply layers are still about 2/3 of the weights inside the big chat models today. The fancy part didn't replace the plain part. It's built on top of it. It was never thinking. It was always folding. The newer designs found a home in science. I'll be watching how far that goes. So if you build with this, tell me what you're seeing. And if this changed the picture in your head, the written version is on my Substack. Let me know in the comments below your thoughts. I would love it. And I'll see you again soon.